Recording. Good afternoon. Welcome to Introduction to Machine Learning with Scikit-Learn. My name is Dr. David Pugh. I am a staff scientist at the King Abdullah University of Science and Technology's Visualization Core Laboratory. I'm joined this afternoon by my colleague, Glendon Holst, who is also a staff scientist in the Visualization Core Laboratory. He'll be helping just make sure everybody gets up and running, doesn't have any issues with the cloud-based software stack that we're going to be using today. And possibly answering a few questions if anything comes his way while he's here. Okay, so we've got a good bit of material to cover today. And so I want to get started. So the first thing I'm going to do is I'm going to start sharing a number of links that we will be using for today. And I'm going to put these links into chat, into the Zoom chat. So the first link that I'm sending around is a link to the GitHub repository, which contains the workshop course materials for both today and for next Thursday. Of course, next Thursday's materials have not been put up there yet because I'm still working on them, but they'll be put in the same place. So link to the workshops GitHub repository. Okay. And so that link has now been put in the chat. So when you click on that link, I'm going to start sharing my screen now. When you click on that link, you'll be taken to this GitHub repository. So it should say KAUST VizLab, which is the Visualization Core Laboratory's GitHub organization. And then the repository is Introduction to ML with Scikit-Learn. And then in the course contents here in the repository, and then also in the README file, there's some kind of information about kind of the rough schedule, what we're going to cover this week, what we're going to cover next week, and some more instructions about how to install the software locally if you want to do that. And I'll talk more about that when we get to the meat of the workshop. The next link that I wanted to share is the link to, just open this in a new tab, is a link to the textbook on which today's workshop and next Thursday's workshop are going to be loosely based on a chapter from this textbook. My favorite kind of resource for getting started with machine learning with Scikit-Learn, Keras, and then TensorFlow. It kind of covers everything, starts at a very introductory level and goes through quite advanced topics. So I'm going to put this link in the chat. I can't type this afternoon, upon which okay, so that link has been put in the chat. Now, I've made today's material and next week's materials are going to be self-contained. So you don't actually need this, this textbook in front of you in order to participate today. But it's a great resource to have, and I highly recommend that you get your hands on it at some point. So if you're on KAUST campus, then if you go to the KAUST University Library, you can search for, let's see, hands-on machine learning, Scikit-Learn. And you should be able to get a digital copy, access a digital copy of this this book online. Yeah, so here it is. So here you can click this and get a full text online. I'm not sure how many people currently can access that full text at the same time. So, If you click on that link and you find that it doesn't work right now, then maybe there are too many people trying to open the book at the same time. I don't know if there's any kind of limit like that, but just generally it's there. So if you're at KFUPM, I asked Rabia if she knew how you could get access to this book, maybe through your university library. She said that she wasn't sure, but that you should be able to request it. So if you reach out to KFUPM, to your university library there, then they should be able to maybe request either a digital copy or several hard copies of this textbook so that you guys can have access to it as well. Okay, so don't need that anymore. Okay, so the next two links that I want to share are the links to the computing resources for today. So the first link that I'm going to share is going to be a link, and actually both of these links are available on in the README file here in the GitHub repository for today's course. So if you're on the KAUST campus or connected to the KAUST VPN, then if you click on the KAUST Binderhub and open it in a new tab, then after 30 seconds or a minute or so, the JupyterLab installation will open in your browser, where all the software has already been installed for you, and it's running here on KAUST hardware, courtesy of the Research Computing IT Binderhub instance here at KAUST. So it should look like this. So I'm going to pass that link now through chat. So there's a question in chat: does the second edition differ from the first? Yes. So as you might imagine, the software in data science and machine learning evolves quite quickly. So after a couple of years, a book gets a bit stale, and so the second edition, which came out in late 2019, I think, is a substantial refresh from the first edition. Not so much in it's a refresh in terms of the code examples work. They use more modern versions of all the software libraries, but like the general ideas haven't drifted that much. But I would encourage you, if possible, to get your hands on the second edition. Okay, so link to the KAUST Binderhub. So again, you will only be able to access this if you're here on KAUST or you're connected via the KAUST VPN if you're off campus. So for those of you who are joining us from KFUPM, you will need to use this public JupyterLab. So if you open that in a new tab, then after 30 seconds or a minute or so, you should get the same thing. The only difference is that the hardware resources on which you will be using are in the public cloud on either that have been donated by either Google or the Turing Institute in the UK, or a few other cloud providers, Microsoft Azure, and some others who have contributed resources to something called the Binder Federation, and I'll mention something more about that in a minute. But it's the exact same resource and software stack. It's just running on public hardware in the public cloud rather than on our on-premise hardware here at KAUST. So I'm going to close this. Since I'm here at KAUST, I'm going to make sure that I use the KAUST Binderhub. But I want to share that link. So I'm going to copy this link. And so link to the public Binderhub. So again, if you're joining from KFUPM, you want to use the public Binderhub. So that's the second link that I sent in the chat, or the one that says public JupyterLab here. Okay, so I mentioned the Binderhub Federation. So the Binderhub Federation is supports the Binder project. And the Binder project is an open source project which turns a Git repository, which could be on GitHub or GitLab or Bitbucket or anywhere publicly accessible, and will turn it into a interactive computing environment running on public donated cloud computing resources. So you put your GitHub repository name here, maybe some other information, and you click launch, and then the Binderhub will copy your GitHub repository, inject it into something called a container, and then run that container and the software installed inside of it inside or on cloud resources. So it's a really great way to share your work that you've done with research colleagues or peers, particularly work that's kind of finished. You can kind of make it available so people can interact with your code and reproduce your research or your work. And it's fantastic for teaching. So it would not be possible for me to teach this course today without a tool like Binder, because installing software for a group of, now we're almost at 80, remotely in this kind of digital virtual session is just impossible. So, you know, hats off to the Binder team for making such an awesome contribution to the open source software community. Okay, so plug for Binder, done. Okay, now I'm going to take a look at the participants. So we've got about 80 of you. Can you just check yes if you have been able to get your Jupyter Lab running in your browser? So you should, in your browser, you should see something like I have here. So if you could just check yes if you've been able to do that, and maybe no if not. And then I will, okay, so lots of people are replying yes in chat, so that's great. If, okay, I see a couple people saying that they're using Google Colab. So that's fine. So if you wish to use Google Colab, like it should work. Not all the software that I have installed in this software stack is installed in Google Colab. And I'm not going to be able to support or troubleshoot that if you get stuck. So that's my only caveat there. So, but obviously Google Colab, for those of you who might not be familiar, Google Colab is another free computing resource that is sponsored by Google. It allows you to run GitHub repositories on Google's cloud computing platform, get access to GPUs and TPUs for free. If you want to do stuff with GPUs and kind of try things out, it's probably the best way to go in terms of getting free access to GPUs, and is probably only financially viable because Google is Google. Okay, so right now I see a couple of no's. So I'm most concerned, so I'm going to go to that. I'm most concerned about the people who have said no. So anybody that I have seen who has said no or has checked no in the participants, I am going to add you to a breakout room where my colleague Glendon will help get you started. So let me just, so you should, when I add you to a room, you should receive like a pop-up invitation that will ask, do you want to join the room? And you should just say yes, and then you can come back in a few minutes. So let me, okay, so I have identified 1, 2, 3. Okay, so I've got about 5 people, either from chat or who have checked. Okay. Yeah, so it might just take a, so I'm going to open the, So I've opened the breakout room now. And so those of you who had checked, had either said no or, so Umar, Salman, so I will, okay, so I've assigned you to the room, Umar, so you should also get a message and just, okay. Excellent. So it might just take, again, a minute, maybe 2 minutes to kind of load. It depends on how many people are loading simultaneously. So Summer is asking a question. I have Anaconda plus Jupyter and the latest Python version installed on my laptop. Can this be used for the tutorial coding? Maybe. I don't know exactly. I know that some of the packages that I've installed and will be using might not be included in Anaconda, would have to be installed separately. So you can try it and see, but I won't be able to support you if you run into trouble, because it's just not feasible to debug local software installations in this kind of a. So I'll share again. So the public binder link is on the README page of the, or on the README of the Introduction to ML with Scikit-Learn. So thanks, Eunice, for sharing the. Okay. So while everybody is still getting set up, so just so that everyone is aware, so these resources will time out after about 30 minutes of completely idle inactivity. So we're unlikely to have 30 minutes of completely idle inactivity at all today, except maybe like at the very early stages while we're going through this logistics and we're just kind of getting started and everybody's getting set up and things. So just make sure to interact with your browser in some way. If you just click a couple of buttons, toggle some things. If you want to start an IPython console and play around with Python, you can do that. Just something to make sure that it stays active. All right, so let me just. So Umar and Wadha, so I see that you've not joined the breakout room. So you should have received an invitation to join the breakout room. And no, so only people who said that they were having trouble getting your Jupyter Lab up and working are people who are receiving invitations to go to the breakout room. So if your Jupyter Lab is working, then you can just ignore, and that's fine. So there's a question in chat. So will the public binder be available through next week? Yes. Yes. So the public binder hub is running 24/7, 365 days a year, with modulus some downtime for maintenance or things like that. So at any time, you will be able to come back and click on this link, open up today's workshop materials in Jupyter Lab running on the public binder hub, and get to work. Okay. All right, so if everybody could just bear with me for a few minutes while I try to sort out the last few people who are getting set up with their software. Okay, so Glendon, I see you're back. Does that mean that you managed to sort everyone out?
I think so. It just was just some people had to wait a little longer, and
Okay.
I think they're all good. They're all back. So
excellent. Okay. Then I am going to, well, I'll just close that room. Okay, great. Okay, so now we should all be back and ready to go. So let's go ahead and get started. So if hopefully everyone will have some familiarity with Jupyter Lab. So this is one of the things that I had mentioned as kind of a prerequisite and pointed you towards some training on the CALS Visualization Core Labs YouTube channel. But just a quick overview. So on the left-hand side is your kind of your file browser, file manager. You can toggle it open and close by just clicking the little folder icon here. And you can navigate by double clicking just like you would with a GUI. So, you can click into notebooks. You can see we have a notebook here that we're going to open in a minute. You can open files. So if you double click on a file, a text file, it will open and you can edit the text file. We'll talk about what this file is in just a minute. And you can start notebooks and start Python consoles. So today we're going to be working in a notebook that I have created for us in the notebooks directory. So if we all double click on the notebooks directory and then double click on part 1, IPyNB, then today's basically notebook, which has everything that we need to talk about today, will open in what's called the main work area, which is just this big space over here in Jupyter Lab. Okay. Okay, so I'm just going to toggle this away so I have more space. Okay, so I appreciate everyone's patience. We've got nearly 80 people with us today, so it takes a little bit to get rolling here, to get everybody set up and have Jupyter Lab running and things. So I appreciate everyone's patience. So what are we going to cover today? So we're basically, between today and next Thursday, we're basically going to cover chapter 2 from the hands-on machine learning with Scikit-Learn, Keras, and TensorFlow book. So the idea is to try to walk you through from start to finish, a complete machine learning project. So today we're going to talk about kind of getting started with a new project and issues about getting data and understanding what information is relevant before you go off and start training models or things like that. And then next week we're going to do all of the kind of model training and talk about how to evaluate models and select one model from a bunch of different candidate models and how to tune a model with hyperparameter tuning, and then and things like that. So today we're going to talk about working with data, understanding the big picture, which is basically how to gather the information that you need to understand the context of the problem that you're trying to solve before you just jump in and start writing code to build your machine learning model. And then we're going to talk about how to get data. And then we are going to talk about some basic kind of data analysis and visualization and understanding your data and understanding the relationships between your attributes or your features and the relationship between those features and what you're trying to predict. And then we'll leave the more coding intensive parts to next week. Okay. So here we go. So the first thing I want to talk about is kind of the importance of working with real data when you're just getting started with machine learning. So the best way to learn how to be a data scientist or learn how to be a machine learning engineer is to learn by doing. And the best way to learn by doing is to work with real world data that is messy and has missing values or is needs a lot of pre-processing and cleaning work to get it ready to have machine learning models trained on the data, because real world data is messy, and it's just something that you need to get used to dealing with. And a good chunk of your time doing data analysis or machine learning, data engineering, things like this, is going to be cleaning data, pre-processing data, combining data sets, feature engineering, getting your data ready so that you can train machine learning models on it. Yeah. So the first thing I wanted to do was just to kind of talk to you about some places where you can go to get real world data that you can practice on. So the first is the University of California, Irvine Machine Learning Data Repository. So all of these data sets that I'm going to show you are public, freely available, open source data sets that you can download and use for either your own research applications, if you're doing research at KAUST or at KFUPM, or if you just want some practice to work on some interesting data sets, then these are going to be good resources for that. So there are currently almost 600 data sets that are maintained by the Center for Machine Learning Intelligent Systems at University of California, Irvine. Lots of classic machine learning data sets that are widely used as benchmarks in the research community are available from here, as well as some other kind of more niche, interesting data sets. There's a data set here about a recent Bitcoin heist and ransomware attack. If you wanted to do some kind of machine learning mapping of Bitcoin transactions, and other kind of interesting things. The next one is Kaggle. So Kaggle data sets. So Kaggle is a, let me just go to their main webpage. So Kaggle is a machine learning competition platform, basically. And it's probably the best resource for practicing and learning machine learning, learning how to do machine learning that I have found. They have competitions for practice that run all the time, like digit recognizing with MNIST or predicting housing prices. They also have competitions where you can win prizes or sometimes cash prizes. They have competitions that are more research focused, where you can contribute to solving some kind of research problem. They often have competitions related to high energy physics by CERN, often some climate and weather related competitions. There was even an earthquake prediction competition a few years ago from one of the national labs in the United States. And all those data sets from past competitions are generally available, and you can kind of search for them by looking through the different competitions here. In addition to the competitions, they also have data sets. And so these are data sets that might not be attached to a particular competition, but that you can download and use for practice and things like that. And they often will have Jupyter notebooks associated with these data sets and competitions to kind of help you get started, learn from examples of others, things like this. So it's also a great learning resource. Next is Open Data Monitor. Whoops. So Open Data Monitor is an EU-based initiative for releasing open source, publicly available data. So it's a good source for European-centric data sets that you can search through and look for different data sets that you might want to practice with or work on. Then we have Wikipedia's list of machine learning data sets for research. So these are probably well focused more towards research applications. And they have a lot of data sets like you can see here. So here's a lot of physical data sets for different things like high energy physics, astronomy, earth science, things like that. So these are typically going to be data sets that are associated with some published paper. There may or may not be links to the published paper, but it's a good reference as well. Next, there is a subreddit on data sets that you can kind of scroll through and find interesting data sets. This one it's a great resource. It requires more effort on your part to kind of dig through the subreddit to try to find to find the data sets, but I did want to mention it because it's a good source. And then finally, Quora also maintains, as part of their answer to this question, a list of freely available data sets that you can kind of scroll through the answers to this question on Quora and possibly find some others. Okay. The next thing that I wanted to mention is that, so all the major cloud providers have repositories of publicly available data sets as well. So if you were to look at Amazon, and these are, they're kind of set up to make it easy for you to get started with machine learning on these data sets, on AWS or on Google or on Microsoft Azure. So if you have, if you have a cloud account with one of these providers and you want to get started, then you might want to get started with machine learning on that platform. This might be a good place to start looking for data. There seems to be a lot of genomics data available on cloud platforms. And of course, depending on what you're doing, you may or may not have to pay to actually do substantial machine learning on some of these data sets. And similarly, you can click the links for Google or Microsoft Azure. The next, or kind of the last thing I wanted to make you aware of is there's a package, a Python package called Pandas Data Reader, which is a companion to the Pandas package, which is what we'll use later today for our data analysis. It's already installed in the software stack that we have, that we're running on here in the cloud. And but it is a package that allows you to connect to a number of different data sources and then download the data straight into your Python session and load it into a Pandas data frame so you can immediately get started. So here's an example of how you could use a platform called Tingo to download some, this looks like stock data for Google, into a Pandas data frame and basically one line of code, and then you could go and do machine learning on that straight away. So Pandas Data Reader is fantastic. I use it a lot myself. It's worth noting that many of these services like Quandl and Tingo and AlphaVantage, they often require you to sign up for an account with their service, and then they'll have some amount of data sets that you can query and download for free. And then if you want to download more data, then you might have to pay. But if you just want to get kind of some daily stock data or things like that, you're generally not going to have to pay for that. And they also may have academic, many of them might have academic plans or things like that. If you're a student, that you can just apply and get access with a university email account for free or things like that. Okay. Now today, our data set that we're going to be working with today and the next week is actually the same data set that is used in Chapter 2 of the Hands-on Machine Learning with Scikit-Learn, Keras, and TensorFlow. I did this because I wanted there to be kind of matching up as closely as possible with what we're going to cover here in this workshop, with also what's in the textbook chapter, so to try to minimize confusion, minimize any confusion that there might be. So this data set is a data set from the US Census in 1990 in California. It has data on what are called census block groups, which is the lowest level of data that the US Census makes publicly available. And it has some social economic data about the census block group, as things like population, median income, median house prices, information about houses in the census block. And what we're going to try to do today is, and next week, is go through from start to finish, a machine learning project to build a model to predict housing prices based on kind of socioeconomic characteristics of using census data from 1990 in California. So, and you can see here is a kind of a visualization of housing prices in California. And if you know anything about housing prices in California now, you'll know that the amount of house price growth in California since 1990 has been just absolutely enormous. And it's kind of a bit ridiculous what houses cost in California these days, and how much less they used to cost in 1990, as we shall see. Okay, so before we move on to the next section, does anybody have any questions about data sets, about where they might want to look for real world data, or if you have some data that you yourself have been looking for, maybe you could kind of toss it out and say, hey, do you know where I might be able to find some data on this topic? And can't guarantee that I will know, but I might know. And if I do, I will try to pass the link off.
David.
Yes.
Are you going to explain how to clean the data?
Yes. So we're going to talk about some of that. The data set for our US California census data is already pretty clean. Some of the data sets from these sources, particularly the ones where you're pulling data from API, are often already very clean, because that's part of the service that many of these are providing. The research data sets will be of varying quality, I would say. It just kind of depends. We're going to talk a little bit of that about data cleaning, but more about data pre-processing next Thursday. So we're going to start with some fairly clean data, because I want to put the focus on the machine learning with Scikit-Learn, and less on the data pre-processing and cleaning, which would mostly be done with Pandas.
Okay.
Okay, so there's some questions about geospatial data. And then, so are there any geospatial data sources? So I will mention, so I'll take that question first. So let's Pangeo. Okay, so if you're interested in doing machine learning and, oh, that's not the right Pangeo. I don't want the Pangeo group. I want, okay. So if you're interested in doing machine learning and data analytics on geospatial data, then you need to be aware of the Pangeo project. So this is a kind of a global open source community for doing big data geoscience based on the Python stack. They work on very large data sets, both geospatial and atmospheric and climate, using many of the tools that have been installed in the software stack that we're going to use today and next week. They also have a mechanism for making data available. So I can't remember where their data is. Let's see. So Pangeo data. Pangeo data catalog. Okay. So, sorry, I meant to send that chat to to everyone. So I'm sending around the link to Pangeo and the Pangeo data catalog. So this is the best resource that I'm aware of for doing data science with geospatial data, climate data, things like that. It's a great group of scientists that are involved in this. They're kind of distributed around the world in various places, using a very modern tech stack and doing a lot of good science. So I hope to do a lot more with Pangeo here at KAUST, because I know we have a large community of geoscientists of various persuasions here at KAUST. So there's a question about, do I know a resource for NLP data sets, sentiment analysis, things like this? There are many of those data sets on Kaggle. So that's where I would start. And also because Kaggle will have, where's my Kaggle? So Kaggle will have many competitions related to sentiment analysis, natural language processing. So you could go through here and find competition data, and you could either join an old competition and work through it as practice and see kind of examples of that kind of analysis. Or if you were to go to data, and I don't know, if we put in like NLP and see what comes up. So there looks like there is a competition, an old competition from almost 10 years ago for practice on getting started with natural language processing and Twitter data. There is a notebook about how to approach natural language problems in different Kaggle competitions, lots of notebooks about how to get started. Here's a data set for natural language processing in the Tamil language. Wonder if there is a NLP Arabic. So here's the data set on handwritten characters for Arabic. If you wanted to do like an MNIST style classifying of handwritten digits, instead of using digits, you could use Arabic handwritten characters. So I would say Kaggle would be your best bet for natural language processing in all languages to get started. And if you want to do research in natural language processing, then there might be better data sets that are available for that, but that's kind of not my area. So I can't, off the top of my head, can't dig out those links. Okay. Okay, great. So thanks for all the questions. So that was a really invigorating discussion on topics related to data. Again, the big takeaway here is get used to working with real world data. There's lots of freely available data that you can get your hands on to practice and develop your machine learning skills. And so now I kind of hope you have some ideas of where you can go to get started for projects. It's particularly if you're you have a master's thesis or PhD chapter that you need a data set for some data analysis, like lots of opportunities to find those kinds of things. Okay, so now so moving on to the next section. So that's kind of the background on data. So the next thing I want to do is talk about getting started with our machine learning project. So the first thing that we want to do whenever you're getting started with a machine learning project is avoid the temptation to just dive straight in and start writing code. So that's like the -- mistake that I think many beginners to machine learning and data analysis, data science, whatever you want to call it, it's the biggest mistake that they make, is that jump in and start writing code straight away. And that writing code before you understand the problem is likely code that you're just going to end up throwing away. And you're not going to get much value out of the time that you spend writing that code. It might feel productive to jump in and start writing code to, build some fancy machine learning model and then run it on some data, but it's not time well spent. It's better to spend the time up front understanding the problem really well so that you can head off in the right direction instead of heading off in a direction that is maybe unrelated to what you're actually trying to do. So our problem is to use California census data to predict housing prices. And again, today we're going to focus on the kind of getting started aspects of the project and understanding our data set aspects of the project. And then next Thursday, we'll focus on the kind of hardcore machine learning, training models, validating models, things like that aspects of the project. Okay. So the first thing that you need to ask before you do any coding or anything like that is you need to understand what is the overall business or research kind of objective of what you're trying to do. So what is your goal? It's typically building the model itself is not the goal. It's not what you're trying to do. You're not building a model just for the sake of building a model. You're building a model to answer a research question or to achieve some business objective. And the research question might be, classify. I need to have an automated process for classifying different types of supernova instead, so I can replace a very labor-intensive process of astrophysicists looking at images from a telescope or telescopes. So that might be one example. Another example might be, you're trying to predict earthquakes so that you can provide an early warning signal to potentially people who might be impacted in the area. Or, if it's a business process, it might be, you want to, increase ad revenue, or you want to, decrease costs in some way. And then the machine learning model that you're going to build is going to be, is going to help you achieve that objective. But the model itself is not the objective. And it's important to keep that in mind because it's very easy, again, to get focused on the technical details of your machine learning model and lose sight of the fact that this machine learning model is not the end in of itself, but like a piece of a larger puzzle or answering some larger question. So in our particular case, and the motivating example I'm using today is, I want you to suppose that we work at a company who is, you can think of it as maybe like an investment hedge fund that invests in real estate in the United States, and in particular in California. And what they're interested in doing is figuring out which houses are available for sale below their market value so they can buy them and sell them at a profit. So they want to make money by flipping houses. So that's basically the company's objective, is to make money by buying and selling houses. So this house price prediction model is actually only one piece of the company's larger modeling pipeline. And so this diagram is to kind of try to motivate that. So, we're going to build this model here. This is just one component of an overall modeling pipeline. And this is something else that is very common in machine learning, that the overall research question or business process that is being addressed is not solved by a single model, but rather a collection of models that interact with one another and feed into one another and create pipelines of models where the prediction of one model becomes an input into another model. So, for example, in our case, we're working with this California census data set, but there might be other data sets that will eventually come into play. And these would be what we would call our upstream components. These would be data sets that would be inputs to our machine learning model. Yeah. And you can think of them as being in some, in our case, they're going to be in CSV files, but they could be in a database or some other storage file system for data, and then we pull from that storage and take them as inputs to our model, and then we're going to make predictions, and our predictions then become inputs of some other model. And then eventually this other model is what actually makes the predictions of whether to buy or sell a particular house, for example. So it's like the takeaway here is it's really important to not forget the research question that you're trying to answer with the model, or the business process that you're trying to optimize with the model, and not get distracted on tinkering around with the model itself, because the model is not the end goal. The end goal is answering some research question or is optimizing some business process or something like that. So that's one takeaway. The other takeaway is that usually your model is only going to be one piece of a larger modeling pipeline. And so communicating with the people who are both providing you the data so that you can understand the data that's coming into your own model, and communicating with the people who are using or consuming the prediction of your model is important, because the whole process has to work together. It's not just your model in isolation. Okay. So moving on. So the next thing that you want to ask is, what is actually the current solution to this problem? So another mistake that I often see, clients that I'm working with or students that I'm mentoring in their machine learning projects, is that they move so quickly to try and to put together their own solution that they don't stop and think about what is the current solution, the current best solution to the problem that they're trying to solve. And it could be that the problem they're trying to solve is completely novel and there is no existing solution. And so, they just have to get on with making, being the first person to solve this problem. But in many cases, there will be some existing solution to the problem that you're trying to solve. And what you want to provide is a better solution along some dimension. So you should at least ask the question, what is the current solution? Both if you're doing this if you're doing machine learning in business or industry, and certainly if you're doing machine learning, to solve answer some academic research question, there is always prior art, prior knowledge, body of literature that you need to be familiar with so that you understand what the current solution to the problem is, and how your solution, which we haven't, which you will design, is better, improves in some way. It's also helpful because, particularly in research applications, instead of comparing, if you know what the current solution is, it's a better benchmark when you start designing your own solution. Because too often I see students that I mentor in machine learning get caught up with comparing the model that they want to build to some ideal model or some perfect model, and how that perfect model would perform, when in fact that's the wrong benchmark, because that model doesn't exist. The right benchmark is whatever the status quo is, or the current solution is. And this current solution might not be very good at all. So it might be a very low bar that you're trying to clear. Another reason why you want to understand the current solution to any kind of modeling problem that you're looking to address is that it helps motivate the type of system that you yourself might want to design. So in the context of our solution for predicting the price of a house, so could be that the current solution for predicting the price of a house is that you completely ignore any demographic information, and then you just predict the price of a house based on a simple average of the census groups or districts that are nearby the census group in which the house whose price you want to predict resides. So it's like the price of this house is some simple average of nearby houses. That's not a crazy way to predict the price of a house, probably better ways to predict the price of a house. But if that's the current solution, then it probably doesn't make any sense to go off and try to design some complicated deep learning model to predict house prices, because you're going to invest a lot of time and energy to possibly come back with an improvement on what is a very simple model. And it would probably have been a better approach to go with a kind of more a simple model that could improve over the status quo to get started, rather than try to jump to some, hugely more complicated model. On the flip side of that, if the current solution to the housing prices problem is that there is already in existence some highly tuned, optimized, gradient boosted machine. I've provided links here in blue. These are links to mostly to the Wikipedia pages to try to provide some background or context if these terms are new to you. We're actually going to train some gradient boosted machines next week. So I'll mention briefly next week into the details of gradient boosted machines, but that'll be next week. But if the current solution is already quite advanced and sophisticated, then it wouldn't make sense to start off with some simple model like linear regression. So knowing what the current solution is helps kind of helps provide important context for what you should do in terms of designing your own solution. Okay. So that's kind of the background. So, always ask, always keep in mind like the big picture, the objective that you're trying to achieve, or the research question that you're trying to answer. Don't lose sight of that. And then always know what the current solution is. I think in the textbook, the motivating current solution for the house price prediction problem is that actually this current house price prediction model is actually, a group of so-called experts on housing prices in California meet once a week and decide amongst themselves about which prices, what they think a reasonable price for particular houses are. And that's obviously very expensive and time consuming relative to some automated algorithm which could predict housing prices. So it's another kind of motivation. Automating and replacing expensive human tasks with algorithms is obviously a classic application of machine learning and data science. Okay, so now we're ready to start designing our machine learning system. So before we can start designing the system, we have to kind of figure out now at a lower level of like implementation detail level, what kind of system do we want to build? So we're trying to predict housing prices in California. We're given some data on characteristics of the house or characteristics of the census block in which the house resides. And we're also given some data on the value of houses in a census block group. So the first thing we need to ask is this a supervised, unsupervised, or reinforcement learning problem? No. And so I provided links here to supervised, unsupervised, or reinforcement learning in case some of you might be unfamiliar with those terms. But in a supervised learning problem, you have data on both features and what are called labels, or your target. And then you can try to find a mapping or a predictive function between your data and your target. In unsupervised learning, you only have information about attributes. You don't have any information about the thing that you're trying to predict directly. And with reinforcement learning, you usually have some kind of a setup where you have some training data, and that training data creates prediction of some kind, which alters an environment, which then can be observed by the model, and then trained again and make a different prediction, which might change an environment, which it then generates something that can be observed by your modeling process. And then around and around you go until you kind of converge to a trained model. So just out of curiosity, so who wants to take a crack at this? Is our house price prediction problem a supervised, unsupervised, or reinforcement learning problem? You can answer in chat. I'll take a look at chat, or you can unmute yourself if you want. Oh, sorry. So there's a question. Someone asked, how can we get this file part01.ipynb? So it's included in your in JupyterLab. So when JupyterLab is running, you should see on the left-hand side here, if you double-click on notebooks, then this file is right here. And if you double-click on it, it will just open the way I have it here. Does that make, so hopefully that makes sense, because obviously you want to be able to follow along with this notebook. And I'm seeing a lot of okay, so great. So there's a lot of good stuff coming through here. So a lot of, I need to figure out how to do polls in Zoom meetings. I've not tried. Well, I guess I could try. So let's see what happens. I'm going to try to create a poll. We'll stop sharing my screen for a minute. I'm going to try to create a poll to see if I can answer this question. I've never done this before, so so let's see how it goes. Is our house price problem supervised? Okay, enter time for the poll. Sorry, almost done. So save. Okay. So I've launched the poll. So I guess you now have gotten the poll, and so you can, yes, I see people answering. So this is great. So let's see. I'll give it a few more minutes. I'll take a look at. I see some people sharing the links to the binder directly. So that's not going to work, I don't think. Because you're trying to share a link to a compute instance that you are running somewhere else. That's not what you, so those links won't work. So if you, the Jupyter, in order to get to the notebook, you need to launch JupyterLab. And then once you've launched JupyterLab, then it's in the notebooks folder. So you just double click on the notebooks folder and then it will be there. I will share my screen again and show you. So when you launch JupyterLab, which you can launch on the public JupyterLab, I'll send this around one more time. So when you click that link to the public JupyterLab, you'll eventually get something that looks like this. And then to get to the notebook, you click on Notebooks, and then double click on the notebook, and it will open up here. Okay. So we've had our poll going for a while. 81% supervised learning. Yes, that is the correct answer. And the reason that it's the correct answer is because we have data on our attributes or our features. So things like population, demographic characteristics, those are our features or our attributes. We also have information about house prices. So we're trying to predict house prices. We have house price data. So we can try to build a model that will map our input data to our house prices. And so that's what makes it a supervised learning problem. All right, so I will go ahead and end the poll. And so what happens if I click share results? So I guess if I'm sharing the results now, so you guys should also all be able to see the results. So we had about 82% with supervised learning, which is the correct answer. So I will stop sharing that, and maybe we'll do another poll to answer. How are we doing on time? Doing okay on time. So the next question. So right, so we're doing supervised learning. So the next question is we need to know, is our house price prediction problem, is it a classification task or a regression task? So is it a classification task? Are we trying to predict basically which category or which bucket our house price is going to fall into, or are we trying to predict an actual house price, a value for a house price? Okay. So is it classification or regression? Okay, yeah, so I'm seeing everybody is regression, 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 exactly. So we're trying to predict the value. We're trying to predict the price of a house as a number, not trying to predict whether a house is like, a particular category, like underpriced or overpriced or fairly priced. We're trying to predict the value of a house. So definitely regression. Are we trying to predict? So now we've determined that we're going to build a regression model. So that's good. Then the next question we need to ask is, so with the regression model, we could build a model that would predict a single value, or we could build a model that would predict multiple values. So that's the difference between regression, univariate regression, and multivariate regression. So are we trying to predict a single value, or are we trying to predict multiple values? What do you think? I'm not going to make another poll. I don't feel like the poll was a little time consuming. I should have made the polls beforehand. Yes, okay, so in chat, lots of people saying single value. That's right. So we're predicting a single value. We're predicting a single house price. So univariate regression problems where you're trying to predict a single value probably are very common, probably much more common than multivariate regression, where we're trying to predict multiple values. But an interesting case that I recently worked on with a client here at KAUST was on predicting load curves for electricity consumption. And there we had this multivariate regression problem because we had all this information about customer behavior and where they lived and weather and things like that. And then we wanted to and past information about how much electricity they had used, and we wanted to predict their 24-hour load curve for the next day based on historical data and then like socioeconomic demographic data. So there we had this multivariate regression problem because we were trying to predict not a single hour's electricity consumption, but a whole 24-hour electricity consumption for the next day. So you will encounter these kinds of multivariate regression tasks in real world problems. Okay. Okay, so great. So we know we want to build a supervised, we're solving a supervised regression task. Okay, the next question has to do with how we are going to use our data. And are we doing batch learning or online learning? So batch learning is where basically you have all of your data. It lives in, you know, a spreadsheet or a CSV file or a database, and you have all the data that you're ever going to need for that problem, and you can learn on that data in one batch, or you can train your model on that data in one batch. Online learning is where, like, you have new data that's coming in all the time, like from a website, or if you're doing like real-time sentiment analysis in Twitter, something like this, or you know, ad revenue forecasting, and you've got you know, information coming in near real time, and you're constantly training the model based on new data that's coming in all the time. So do you think we're doing batch learning or online learning here? And I see a lot of people saying batch. Yeah, that's right, batch learning. So we have our CSV file data, which I haven't shown you yet, but I've mentioned. And we're going to read that in, and we're going to train a model on that data, and then we're going to use it to do some prediction. So batch. Okay. So these are important because they help. The space of machine learning algorithms is vast and growing. And so you need to know the answers to these questions so you know to basically start looking in the right place. So we know that we're solving a supervised regression task, and we're doing batch learning. So automatically, we have eliminated a huge part of the machine learning modeling space from consideration, because we're only going to look at models that are suitable for solving supervised regression tasks and that are suitable for batch learning. Okay, so you need to kind of learn to answer these questions and think about them whenever you approach a new machine learning problem. So now that we've done that, the next thing we need to do is pick a performance measure. So by performance measure, we mean, so how are we going to measure our model's error? And therefore, like, how can we decide whether our model is any good or not? So what's going to be the metric by which we determine whether our model is performing sufficiently well? Now, if there is an existing solution, then you may have to just inherit whatever metric is currently being used by the existing solution, because that's going to be the natural kind of benchmark for whatever solution that you're going to create, you know, is going to be the current performance. For regression tasks, a very common performance metric is something called root mean squared error. And I put the mathematical formula here for root mean squared error. But it basically, so this is the root mean, the way that you should interpret this is the root mean squared error given a data set X and some machine learning model H. And the way we compute this is, for the machine learning model, we pass in each sample of data, and that makes a prediction. In our case, it's going to be a predicted house price. And then we're going to look at the difference between the predicted house price and the actual house price, and then we'll square it so that we make sure that we're dealing with always positive numbers. We'll sum them all up, and we'll divide by the number of training samples that we have. So we're going to compute an average of the squared errors. And then we just take the square root to kind of undo the square, if you want to think of it that way. So we have, so the units of our root mean squared error are not like dollars squared, but dollars in our context here. So that's a typical performance measure for regression problems. Now, actually, Scikit-Learn has a whole bunch of different metrics. So if you click on this link, you can see here that there are a huge number of different metrics and scoring functions that can be used for your machine learning problems. And you can see, so there's some metrics for classification. So we know that we're not doing classification problems. So we can just completely ignore all of these right here. Similarly, we're not doing clustering, which is a type of unsupervised learning problem. So we can just ignore those. So, but then we get to regression. So we are doing a regression problem. So, so a regression problem has, a number of different kind of metrics that we could use here. And so you could look through here and click on these links if you're unfamiliar with the different documentation. So there's so negative mean squared error. So that's just, the negative of the mean squared error that we've been talking about, or the negative root mean squared error, which is just, again, the square root, but then with a negative in front of it, and a whole bunch of different ones. This is R squared. So this is if you've taken any statistics courses, you've probably talked about the R squared of a regression. So you can use the R squared as a measure. So there's a question in chat. So how do you specify the value of the root mean squared error that is correct? So, so one way that you could think about that would be to say that, well, if you had a model that predicted perfectly on your data set, then the root mean squared error would be 0, because if your function h that predicted well, the input data was kind of perfect at predicting your training data, then it would have a 0 for each of these differences between its predicted value and the actual target value. And so when you add them all up, you'd have 0. If you ever had such a function, then you might ask yourself whether this would actually predict well on new data that were not included in the training data set. Because typically, if you have very, very, very small root mean squared errors, you might think that that's very good, but as we'll see some examples next week when we actually train some models, that typically means that actually you have just memorized your training data set, and when you go to try to validate or test your model, it's not going to perform very well on data that it's not seen, because it's suffering something called overfitting. But we'll talk more about that next week. So I put this link here so that if you wanted, you could kind of go through and look at what metrics were available in Scikit-Learn to start to familiarize yourself on with the documentation of Scikit-Learn, because we're going to start using it now and then use it heavily next week. So Azara has a question: is there any tolerance on the root mean squared error? And I guess by tolerance, you mean like, is there any value that is considered to be too large? So again, so smaller root mean squared error is generally going to be better, but there's a caveat to that about overfitting, but we're going to talk about that next week. But there is no absolute correct best value for root mean squared error that you're trying to hit. It's always going to be a relative comparison. So we might fit many different candidate machine learning models, and then we will use the root mean squared error to kind of compare them relative to one another and look for the model that has the lowest root mean squared error that is not overfitting or memorizing the training data set. And we're going to talk more about that next week. So you can actually execute this cell in your Jupyter notebook if you hit Shift and Enter. So this will import the metrics package whose documentation we were just looking at. And then you can type metrics dot, and then if you hit tab, might have to wait a minute for the autocomplete to load. So for some reason, usually if you hit dot and hit tab, then you should get a drop-down menu of all of the examples or all of the functions that are available in the metrics package. So in particular, here's mean squared error. Yes, so if it time, so there's a couple of questions coming on chat about what happens if the public Binderhub disconnects. So yes, I mentioned that earlier, like it will disconnect. You can just go back and click the link again and open it. It should not, if you're actively using it, it should not time out for many hours. But if you leave it idle, it will time out after about 30 minutes. There's another question about root mean squared error. So for given features, root mean squared error has a unique solution minimizer. And yes, so that's true. So the problem as formulated is something called a convex optimization problem, and it does have a unique global minimum. But that's a more deep dive into the maths than I'm planning on doing today. So if we do, I think the root mean squared error, what is it called? Oh, the negative root mean squared error, yes. So this is why well, my tab completion is not working today, so I'm not quite sure why. Okay, but this is what the documentation looks like for most of these metric functions are similar. So we have the true values for the target that we're going to try to predict, and then the predicted values. So the true values are going to come from our data. So these are going to be our house price data. And then the predicted values are going to be what our model is going to provide. And so eventually we're going to compute the value of this metric for our different models by training our model so that it can provide true predictions of house prices, and then we're going to compare them with the true values. And then the formula for computing the mean squared error is basically going to be what's underneath the square root symbol here. So again, this is kind of a preview of the kinds of things that we're going to do next week. I just wanted to show you how to import things and how you can look at documentation in your Jupyter notebooks. Okay. The last thing that we want to do is check our assumptions. So we've gone through and we've answered all these questions, so we know kind of what we're dealing with. We're doing a supervised regression task. We're going to use batch learning. We've decided that we're going to use a particular metric like root mean squared error. You know, I would encourage you to go through these metrics, you know, over the next week. Maybe you can pick a different metric like that would still be appropriate for regression, and maybe we can try comparing outputs of different metrics for different models next week to try to understand the impact of the different metrics, if you want. So now we need to check assumptions. And so what do I mean by this? Well, so our model is, you know, one piece in the modeling pipeline. So we've answered these questions about, you know, supervised regression tasks, batch learning, but we should probably make sure that those answers are correct. So for example, we could go to the team that is managing this downstream model, this model for investment analysis, and just ask them, you know, how are you using our house price predictions? So they might say that, well, actually, we don't really even use the house price predictions values directly, but what we end up doing is taking your predicted house prices and just kind of bidding them into, you know, undervalued, fair market valued, and overvalued. So in that case, you should kind of stop and say, okay, well, if the team that is building this investment analysis model just takes my numbers, my house price predictions, and then turns them into categories of underpriced, fairly priced, and overpriced, then why don't I just build a model to basically predict whether a house is underpriced, fairly priced, or overpriced directly? In which case, that would no longer be a, so yes, so sorry to interrupt. So yes, we can have a break in just a moment. Thank you for letting me know that prayer time is coming up. It'll be a good time to take a break. So if this investment analysis team, again, is converting our numerical predictions into categories, then we should probably just predict the categories directly. In which case, instead of building a regression model, we ought to be building a classification model. Because instead of predicting house price numbers or house prices, we are predicting whether a house is undervalued, fairly valued, or overvalued. So that's just an example of, again, the thought process that you have to go to just double check that you're on the right path. So if we stop for a break at 2:45, would a 15-minute break be sufficient for those of you who will be going to prayer? Okay, excellent. So we'll plan to do that. So we will stop at actually, to be honest, now would be a good place to stop, because the next thing that we're going to do is talk about the software environment and getting the data and things like that. So rather than rush through that, so let's so let's stop here, and we'll have an extended break for those of you who are going to pray, and we'll start again at 3 o'clock. How about that? Rather than trying to rush through something to fit it in before people need to have their prayer break. Okay, cool. So we're going to do that. So I'm going to pause the recording, and then we will pick up at 3 o'clock. Be wary. Try to keep your binder instances active so you don't lose them if possible.
I have a question if I can.
Yes.
Because I may not be able to come. I may come, but a little bit later than the break.
Okay.
So I managed to build the everything locally, except for one package.
Okay.
I don't know what's wrong with it. I know you said you will not support it, but so this XG boost.
Yes.
I wasn't able to use it, to download it.
What?
It says the package cannot be found or something.
What operating system are you using?
Windows.
Windows. So
everything else is fine. I managed to launch the
okay. In
the Jupyter Lab and everything.
So off the top of my head, I don't have a Windows computer myself. So I don't use them that often. So it could be that XGBoost is not available for Windows. But that's okay. So we're going to use, so XGBoost is a...
No, it is available, but I need to build it or pre-build it first, I think.
Oh.
Which I can do following the instructions in their website, but it's not out of the box will work.
Yes. Okay, I see. It's not going to be critical. So there are other implementations of gradient boosted machines that are in Scikit-Learn directly, and we'll probably use those. I included XGBoost in the software stack because it is widely used, and I wanted to have everybody set up with as much of the relevant software as possible. I'll have a look around over the next week to try to understand what the issue is with Windows, and maybe there's a way that I can actually change my setup here so that it will also work on Windows for XGBoost. I'll have a look and see.
Okay, thank you.
You're most welcome. Thank you for letting me know. I had no idea that that was an issue. Any other questions before we break? Nope. Okay, so I'm going to pause the recording now. And we'll pick it up in about 20 minutes. So at 3 o'clock, we'll start again. Okay? Bye for now. Okay, so welcome back, everybody. Hope we had a nice extended break. So now I'm going to pick up where I left off, and we will probably push on through until we're finished with what I wanted to cover today. And then I'll try to leave some time for Q&A at the end. At the end of the day, so we won't go all the way up until 5. Okay, so I need to share my screen again. Okay, so we finished kind of checking our assumptions. So now we're going to actually start working with the data. So everything that we've done up until now was a lot of just like general kind of motivation, general kind of helping you get started, helping you think about and answer questions that you need to ask when you're starting any new machine learning project, and kind of providing some motivation for the project that we're going to work on for the rest of today and then next week. So now we're going to get into the more technical topics. So now we're ready to start working with our data. But before we can start working with the data, we need to get our software stack set up. Now, fortunately, our software stack is already set up for us, and we're running in the cloud on Binder. But I wanted to walk you through just the different configuration files and the instructions for setting up the software stack locally, and also where you can go to get more training about how to use the tools that I use to build this software stack. Because being able to manage your own software stacks for your machine learning project is a key skill that you'll need to develop in order to be successful. Okay, and that's kind of what I have here under this create the workspace section. So if we look at the README file, so this is just the README file, the same README file that's in the GitHub repository. But in the GitHub repository, I mentioned some instructions for how to use Conda, a tool called Conda, to create an environment, a software environment, where all of the software is installed based on software listed in several files. So there's this environment.yml or .yaml file, a requirements.txt file, and then a post-build script. So these configuration files contain all of the software that we want to install, and then we use a tool called Conda to create environments and install our software. So that's the tool that I use in all of my projects to manage my own software environments and to install my own software packages for all of my machine learning projects. I teach a course here at KAUST on using Conda for data science and machine learning. There's a link here to the training materials for this course. I've taught this course twice this semester here at KAUST already. The videos of those workshops are on our YouTube channel. You can watch them and kind of follow along, but the course materials are here. So if you're not familiar with Conda, I highly recommend you take a look at these training materials, watch our videos on the YouTube channel. It's an important tool that you need to learn how to use effectively to manage your own software stack for your machine learning projects. So with Conda, we can write down our software dependencies in something called an environment file. And so this is the environment file that I have created for the software stack that we're currently using in the cloud. And it has a number of packages that excuse me. It has a number of software packages. I just kind of want to walk you through these packages to help familiarize you with the Python machine learning ecosystem a little bit more. So there's a question from Nabil. So is using Anaconda the same? So Conda is a tool that is provided along with Anaconda and Miniconda. So yes, so if you have Anaconda installed on your computer, then you will already have the Conda tool. You may need to update it to the most recent version, but you will have that tool on your system. And it's available for Windows, Mac, or Linux. So I just want to walk you through some of the software that we've installed here. So the first one, I'm going to kind of do this a little bit out of order. So I'm going to try to start in the more basic packages and then work my way up. So Pandas is the kind of one of the core data analysis libraries for working with tabular data in Python. So there's a great book called Python for Data Analysis by Wes McKinney, who is one of the creators of Pandas. Has a second edition that just came out very recently. Highly recommend that book. It's a deep dive into pandas and data analysis in Python, but this is kind of one of the key libraries for doing data analysis in Python that we're going to be using. So version 1.1 of Pandas is installed here. Now, next is Scikit-Learn itself. Actually, we've got the Scikit-Learn documentation here. So Scikit-Learn is a kind of the classic machine learning library for Python. And what I mean by classic machine learning is I simply mean not deep learning. So Scikit-Learn is kind of where you want to start if you want to do your classification, regression. Those are supervised learning algorithms. Clustering is an unsupervised learning algorithm. They have tools for things like dimensionality reduction, model selection tools, data pre-processing. So we're going to use a lot of these different packages next week when we actually train our house price prediction models. Now, if you want to scale Scikit-Learn and Pandas models out to take advantage of multiple nodes in a computing cluster, because you have a really large problem, then you're going to need to use a tool called Dask. So Dask is scalable data analytics in Python. So Dask takes kind of the Pandas and NumPy and Scikit-Learn packages, which are kind of widely used and kind of the standard packages in the CPU-based machine learning community within Python, and allows you to use those packages but scale your computation across multiple nodes in a cluster. So if you have a really big data problem, then Dask is probably like the place that you want to start for large-scale CPU-based machine learning. And so we've also installed Dask in this software stack. So I'm not going to go through all of these. So LightGBM and XGBoost are packages for doing gradient boosted machines. So I'll talk about those again next week when we get to actually fitting different kinds of models. Optuna is a package for doing hyperparameter optimization. So that's for tuning your model. So once you've identified a model that performs well, but you want to try to make it perform a little better by tuning some parameters of the model, then you can use Optuna to do that. We'll talk about hyperparameter tuning next week as well. What else is in here? So there's a library called Feature Tools, which is for automating the process of feature engineering. Also something that we're going to talk about next Thursday. But that library is here. So what I've tried to do is try to provide you with, we're not going to use all of these tools next week. A lot of these tools are very advanced and can scale up to, cutting edge machine learning application and use cases. But I wanted you to see how they could be installed should you be interested in using them in your own projects and own use cases as you become more proficient at in your machine learning. So it's basically just making you aware that these kind of tools exist. Another interesting one is Numba. So Numba is a just-in-time compiler for Python. It translates your Python code into fast machine code that can target CPU or even GPU hardware architectures and significantly speed up your Python code. So it's another library that you should just be aware of in case you find that you need to speed up some code. You might try Numba as a way to do that. And I've installed Numba here. Now, not everything can be installed with Conda. There are some packages that are only installable via a tool called pip, which is the default Python package index or package management tool. This is pip. And we installed pip with Conda. So pip is installed in this environment, and then we use pip to install things that are not available via Conda by listing them in this requirements.txt file. So the requirements.txt file here just has a couple of packages. This is a package for something called ensemble learning, which I might mention next week. And then this is something for trying to understand what features are most informative in your machine learning model. So like what's driving your prediction. So it's helping you, it's a package called SHAP, which helps you understand your machine learning model a little bit more. It's a method for understanding machine learning model using something called shapely values. Okay. And then so I have written this little script, which basically, it's a bash script, which runs and uses this command to create a virtual environment for your software stack using Conda, and based on the dependencies listed in the environment.yaml file, and then activates it and then runs this post build script, which contains some dependencies for Jupyter Lab, which is the environment that we're using here. So I've installed some extensions to Jupyter Lab that will kind of enable different features and things like that, also as an example of kind of how to do this. You're not meant to necessarily understand all the moving pieces of this kind of software stack, but I wanted you to see them and just kind of listen to me talk through the different pieces and how they fit together, so that after this is over, you can go watch the recording. You can kind of walk through the steps on your local machine and kind of understand what's going on. And again, being able to manage your own software stack with tools like Conda and pip is a big part of being proficient with machine learning and data science. And again, there's the link to the teaching materials on Conda and pip, and the link to the YouTube channel, which has recordings for both of the workshops I've offered at KAUST on Conda this year. Okay, so that's all I'm going to say about the software environment. Does anyone have any questions about the software environment that you want me to discuss, or any issues that you want to discuss? Otherwise, we'll move on and download the data and start looking at the data. Oh, Going once, going twice, sold. Okay. So what I've written here in downloading the data, so the data file itself has been made available by the author of the textbook via his GitHub repository for the textbook. And this is just a little function that will download this. It will actually check to see if this file exists. So there's a data folder in the repository that has a housing directory, and inside that housing directory is this gzipped data set, which I've already put there so we wouldn't have to download it, just in case there are any internet issues or things like that. But this function will basically check whether this file exists, and if it doesn't exist, it will download it. If it does exist, or once it exists, it will basically just extract it. So if we hit Shift and Enter, which will execute the code in this cell, and then we hit Shift and Enter again to run this fetch data function, it didn't need to download the data because it was already there, but it will have unpacked this housing.csv file. And if you click on the housing.csv file, you'll see, so this is actually our data set. And we can just kind of look at it and see that, okay, we've got some longitude, latitude, housing median age, total rooms, total bedrooms, population, households, median income, median house value. So this is the house price that we're going to try to predict. And then something called ocean proximity, which looks like it has some text which says how close the houses in the census block are to the ocean or the bay. Okay, so that's our data set. So we've automated the process of fetching our data set, which is useful. And now we're going to load the data. So again, we're going to be using this Pandas library to load the data into something called a Pandas data frame. And again, I've got a link here to the Python for Data Analysis book by Wes McKinney, which is how I learned Pandas on the first edition of that book. So again, if we hit Shift and Enter, then this will load the data set. And we can just take a quick look at the first few lines of the data set by, again, using Shift and Enter to execute the cell. So each row in our data set represents a census block group or district. So what we have here is, so the median age of houses in a particular census block group, in the particular census block group with these lat-long coordinates, so latitude, longitude, and latitude coordinates, for the census block group somewhere in California, had a housing median age of 41, had 880 total rooms, 129 total bedrooms. These are totals across all the houses in that census block group. And then population, not clear what the units on population are. Is it actual like numbers of people or something else? We're not quite sure. Number of households, median income, so 8.325. So that's clearly unclear. Oh, wow, it's unclear what the units are there. Is that dollars? Probably not dollars. A median income of $8.32 is not very much. So there must be some other units for the median income. Median house value is plausibly dollars. So this is saying that the median house value is $452,000, or $452,600, which is probably in dollars. And then this text data, ocean proximity, so near bay. So it's always a good idea to take a quick look at the first few lines of your data just to try to see what's there. And to make sure that it looks like the data has been loaded properly into the Pandas data frame. So there's a question about uploading the data. Sure. So to upload to get the data, all you have to do is you need to hit Shift and Enter, or you can actually hit, so if you if you click anywhere in this cell, you can actually hit this play button, and that will execute this cell, the code in this cell. So that loads the function fetch data. And then in the next cell, if you click this play button, or you can click in the cell and then you can hit shift and enter, that will fetch the data. Reloading the page is not, so nothing, what should happen is when you run this fetch data, it executes the code in this function, which actually just extracts the file that already is available in your on Binder, and then creates this housing.csv file. So if you look in the data housing folder, you should see a housing.csv file. So if you've not seen that, if you're not seeing that, then I think Glendon is not here at the moment for me to put you into a breakout room. So you'll just have to kind of follow along on my screen and then try to sort that out later. And remember, since we're coming back from break, if you feel like it could be that your Binder instance has died or timed out maybe over the break. So you might have to go back and click the public Jupyter Lab button. Okay. So I'm going to put the link to the public Jupyter Lab in case your compute timed out. Okay. Okay. So we can just look at our data. And so then the first question that we want to ask ourselves is what types of data are we working with? So are we working with numerical data, or are we working with non-numeric data? And so we could kind of glance at the first few rows and we see, well, most of these rows are numeric data except for this ocean proximity column. So let's try to see more about the ocean proximity column. So there's a method called info on a Pandas data frame. And this gives you information about the data types and also whether you're missing any data, things like that. And what you can see from this is that all the columns have float 64, so they're numeric, except the ocean proximity. And we suspected, obviously, that we could see it has text data here, so it was not going to be numeric data. We also see that there are 20,640 data samples in our data set, and that most of these columns do not have any missing data except for total bedrooms. So total bedrooms has missing data. So it doesn't have, there are some census block groups that don't have information on total bedrooms. So that's something that we'll have to deal with. We'll have to, many machine learning algorithms don't like missing data. So you either need to do something called like imputing. So you need to either find a way to fill in values for those missing data, or you have to drop the data samples that are missing data from the analysis. We'll talk about exactly what to do with that probably next week, next Thursday. So we see that there's this ocean proximity variable. So we can actually use this code to select out, I'll delete some of this. So this is the syntax in Pandas for selecting a particular column of data. So we're going to select all the rows and then the ocean proximity column of the data. And then we can use something called value counts which is a method for Pandas series, which will basically count the number of times a value occurs in this column of data. And so if we run this, then what we see is that we have 5 census block groups which occur on islands off the coast of California. And we have 2,290 that are near the bay. So that's probably like the San Francisco Bay area. 2,600 that are near the ocean. 6,500 that are inland, so that are not near the ocean at all. And then we have, 9,000 that are within an hour's drive of the ocean. So if you think about this, like, people like to be near water. And so it's fair to wonder whether, if you're, again, we're thinking about, we're going to be building a model to predict housing prices. So plausible to think that there could be a relationship between the distance of a house from the water and its price. So in particular, you might suspect that housing prices will be higher if they're close to the water, close to the bay, close to the ocean. So that's something to think about. So now we're starting to look at the data, and we should be thinking about, okay, we want to build a model to predict housing prices. So we're trying to get a feel for what relationships in the data we might be able to use to predict housing prices. Okay. But also we should see here that actually there are only 5 islands, or 5 census block groups that are on an island. So 5 observations are probably not going to be enough data to help us make useful predictions about the impact of being on an island in terms of its impact on housing prices, things like this. Okay. So the next thing that you want to do is compute some descriptive statistics. So the descriptive statistics are, so if we hit Shift and Enter, so this is going to compute descriptive statistics for all of the numeric columns in our data set. And so this is what we do when we want to find out, like, okay, well, what is the mean, standard deviation, the minimum values, the maximum values, the interquartile range, which is the difference between the 75th and the 25th quartile, the median, so that's the value in the data that where 50% of the data is less than that value and 50% of the data is greater than that value. Can be useful to look for maybe not so much outliers, but what are extreme values in our data. So this is usually like the first thing that I run after I've looked at the first few rows in the data, and I've looked to see whether there are any missing values and what kind of data types we're working with. Then usually I'll run value counts on any non-numeric data to see kind of whether or not they look like there's enough data in these non-numeric columns to actually be useful. Also, it's good to think about non-numeric columns because machine learning models typically work with numbers. So if you have data that is text in nature, you have to think about, how am I going to encode the text data into numbers of some kind? And there are a few ways that you can do that. There's something called one-hot encoding, which we can talk about next week when we actually do the training of the models. And there's something called ordinal encoding. So there are different ways that you can approach this. But at the end of the day, if you have text data, you're typically going to have to find a way to convert that text data to numbers before you can apply machine learning algorithms. Okay. Okay, so we did some basic descriptive statistics. Now, the next thing is plotting. So you always, always, always want to plot your data in many different ways and look at it and try to understand visually, because your brain is a good visual pattern recognizer. And so it's good to make plots of your data. So the first thing we're going to do is plot a histogram of the median house value. So this is a histogram of our target. This is the thing we're trying to predict. So here we're going to see a histogram of the variable that we're trying to predict. And make this just a little bit smaller so that it fits on the screen. And so what does anybody want to mention something that they see in this histogram that looks a bit odd to them? You can mention it in chat, or you can unmute yourself and give an answer if you want.
I mean, the last peak, the maximum, looks weird.
Yes, it does, doesn't it? So if you think about, this is like the distribution of house prices. So you think, okay, well, there's not very many house prices down here that are very low, and then we've got this huge number of houses that have prices that are, 100, somewhere between 100 and 200,000, so maybe 150,000. And then as you get more expensive, the number of houses goes down, as you would expect. And then all of a sudden, at 500,000, you have this huge spike. Yep. Now, Mohamed has figured out the answer to this, which is that housing values are capped at 500,000. So the census data, the US Census collects data on housing prices, but then they will compute the median of housing prices within each census block group and report that. But if the median number is greater than 500,000, they just write greater than 500,000, or they just write 500,000 and leave it. So this could be a problem because we're actually trying to predict housing prices. So like all of the census block groups that have median house prices of 500,000, we know that data is not correct. Those census block groups probably had values that were, or median house values that were substantially higher than 500,000, but they got truncated because of the way the data was collected. So this is a great example of understanding how your data was collected to try to help inform how you should handle processing this data. So, we have to think, do we want our model to be able to predict house prices that are higher than 500,000? Or do we want the model to never predict a value above 500,000? What do we want to do? Answering this question might involve talking with the team who is going to use the predictions of our house price model as inputs to their model. And we'll talk about ways to deal with this. But right now, the point is about plotting your data so that you can see things like this and start to think about issues that you're going to have to deal with before you can start training machine learning models. Okay, so here, I picked out a particular variable to compute the distribution with a histogram, but we can actually just compute a histogram on the entire data set, and it just computes histograms for all the variables. And since we don't have a huge data set here, we can do this and it doesn't take very long. So we have longitudes and latitudes. So what do we notice about longitude and latitude here? What's the kind of the thing that jumps out at you when you look at the longitude and latitude? Anybody want to? Bimodal, yes, exactly. So it's bimodal. And so remember, we're dealing with California here. So if you think about California, there is a really big city in Southern California called Los Angeles. And then there is a big city in Northern California, San Francisco. And so I'm not going to go and check the map, but I would venture to guess that these two peaks correspond to the large numbers of census districts that are in and around the highly dense areas of Southern California and the San Francisco Bay Area. So that's going to correspond to these peaks here. So what about housing median age? Any thoughts on housing median age? So this is the median age of a house in particular census group or census block. There's a couple of things here. What are your thoughts? Yep, so Basel, yep. So again, it's the same issue from that we saw here. It looks like the housing median age was just truncated. So any house that was over, say, like 50 or 55 or something has been lumped together. Exactly. That might be an issue that we need to deal with. So something to be aware of. And the other is that it's kind of a little bit bimodal. So you've got ignoring this cap, which is an artifact. You've got houses, a lot of houses that with a median age of like, maybe let's call it roughly 15 years, and then an older median age of about 35 years. So it seems like there was some like housing booms historically in California where there's a big boom about 35 years ago, and lots of houses were built, and then about 25 years ago, and then 15 years ago. So looks like every 10, 15 years there seems to be a boom in house prices or housing builds, the number of houses built. And it could be that this might have an impact on the price, because it may be, maybe their older houses were built with, to higher construction standards or something, and and therefore these older houses actually hold their value better than newer houses. Don't know, but it's certainly possible. Okay, so median house value already looked at. So there's kind of something about the total rooms, total bedrooms, population, households, and median income that I want to see if you can spot. So does anybody have an idea about kind of a common feature between in the distributions of these 5 variables? There's actually, I guess, kind of two things that I want to see if you guys can spot. Kareem, yes, third moment, skewed. Yes, they are skewed. So they have very heavy right tails. So that there are some values that have very large, total rooms and total bedrooms and population. And yeah, so Ahmed says, is it a power law? Possibly. So some of you are kind of getting a bit more precise than what I want to go for. So skewness is what I want you to take away from this. They're skewed to the right. So they all have these right tails over here. And a lot of machine learning models, the theory underlying why the models are useful and why you might want statistically useful often assumes that the variables that are in your data are normally distributed or follow a Gaussian distribution, which is like a bell-shaped kind of distribution. These are not bell-shaped. So that means that we might want to think about doing some pre-processing to transform these distributions so that they are more normal, more Gaussian, more bell-shaped, before we actually start training machine learning models on them. Otherwise, we might not get terribly good results. Now, the second thing is the scales. So, total rooms, total bedrooms, median income. So median income ranges from 0 to 14 and something. Total rooms goes from 0 to 40,000. population goes from 0 to 35,000. So, and then, you know, our latitude and longitude, you know, have a very narrow range. Housing median age goes from 0 to 50. So many machine learning models expect your input variables, your data, to consist of variables that have similar scales. So we need to be, when we see scales that are wildly different, we need to think, okay, I'm going to need to rescale my data so that the input variables all have similar scales before I train machine learning models on them. Okay. And we're going to see how to do that on Thursday, next Thursday. So Nabil asked a question, how can a house have total bedrooms in the hundreds? Good question. So this is the exact kind of question you should be asking. The answer is that these variables are totals for the entire census block group or a census district. So so the median income and the median house value are kind of the median of house prices in a district and the median income in the district. But these rooms are like the total number of rooms in all houses in a district, and the total number of bedrooms in all houses in a district, and the total population in the district, and the total number of households. So we might want to think about how we could recombine these variables in a way that might make more sense. Because, like, does it really make sense that the median house price in the census district should really depend on the total number of bedrooms available in that census district? Probably not. It might, I mean, you think the price of a house probably does depend on the number of bedrooms in that house or the number of total rooms in that house, but not like the total number of rooms in all the houses in the area. So we have to think about how we might combine these variables together to extract more meaningful, to create more meaningful variables that might be more predictive of housing prices. That's a process called feature engineering. And we're going to do a little bit of that today, and that's going to be kind of the bridge into next week, the feature engineering into the data preprocessing. And so someone from KFUPM, would you please elaborate more on similar scale? Sure. So what I mean by similar scale is look at the horizontal axis. So our longitude ranges from -124 to -114. Our latitude ranges from like 30 to 42, something like this. Housing median age ranges from 0 to 50. So these ranges make sense given the variables. I mean, these are degrees longitude, degrees latitude, median age is in years. So I mean, these ranges are sensible. But if you were to put variables that have different scales, different ranges into a machine learning model, then a lot of machine learning models are basically optimization models. They transform fitting parameters into an optimization problem. And mathematically, if your optimization problem has inputs that have wildly different scales, it makes it a lot harder for the model to kind of find the minimum or the maximum set of parameters, depending on whether you're minimizing or maximizing your objective function. So you want your variables to have similar scales. So one thing that we could do is we could actually rescale all of these variables so that they range between 0 and 1, just as an example. So we could basically go through here and divide and basically just reshift the scales so they all had scales between, or they all had the same scales between 0 and 1. There are many different ways that you can apply scaling algorithms, to rescale your data so that they have similar scales before you feed it into the machine learning algorithm. And that's a very important kind of pre-processing step. We're going to talk about that next week on Thursday. But this is where we see that this is going to be a problem that we're going to have to deal with. We'll see how to deal with it next week. Okay, so let's see. So I put here, let me see if I missed anything in my, no, I think we hit on all of the issues that I wanted you guys to spot. So well done. You guys managed to spot all of the issues that I spotted with this data set. Okay. So now what we need to do, so now we've looked at our data set, we kind of have a feel for what's going on. Now, before we do anything else, we need to split our data set into a training data set and a testing data set. And our testing data set, we're going to set aside and we're not going to look at it again until the very end of our process. And the reason for that is to guard against something called overfitting. So if we just take all of our data and train our model on our entire data set, then we don't have any way to compare different models trained on that data set. We need to, and there's a real danger. Not only can we not compare different models on the data set, there's a real danger that our models are just going to memorize our data set, and then when we try to predict the price of a house given some new input data, it's going to give us a really bad value or really bad prediction, and we'll have no way to test whether that prediction is any good. So we always split our data set into training data and testing data, and we're going to put our data set, our testing data set aside, and then we will come back to it at the very end of next week when we finally decide which of our candidate models is the best model that we want to use for our problem. So now we're going to talk about how do we actually do that. What's the process for splitting a training data set into a training data set and testing data set? Okay. So the first question that you need to ask is, are you working with all the data that you're ever going to have, or, which is often but not always the case in batch learning, or in the future, are you going to have more data? So if in the future you might have more data, so for example, let's instead of just having this CSV file of housing data, the census data, let's suppose we were pulling this data from a database, and that database was going to be constantly refreshed, and new information was going to be put, new data was going to be put into that database. And then every time we would go back to train a model, we would be pulling data from this database. Well, in that case, we want to make sure that every training sample every sample of data in our data set needs to consistently either be in the training data set or in the testing data set. We don't want to be constantly going back and pulling a new set of data into our training data and a new set into our testing data, because eventually, if we do that over and over again, it's like randomly sampling our data from our data set. We're effectively going to see every data point, and our model is just going to memorize all of the data, which is not what we want. That would be overfitting, and it won't. Our model won't generalize very well. So we want to make sure that we get the same training data set and the same testing data set, and that any new data that's added consistently is included either in the training data set or in the testing data set. And the way that we do this is by creating a unique identifier for each training data point, and then doing something called hashing, which takes this unique identifier and kind of pseudo-randomly gives it an integer number. And then once we have these pseudo-random integers associated with each of our training or each of our data points, then we can kind of use those random integers to divide our data between training and testing, and we can be guaranteed that every time we reach into our data to get more training data, a data sample will either end up in the training data set or the testing data set all the time. It will never move back and forth between training and testing. Now, that's a bit subtle, and as I was kind of listening to myself explain it, I'm not really sure that I got it across very well. It's covered in more detail in the chapter. I guess the important takeaway, at least for practical purposes, is that we're not going to have to do that here, because we have our housing price data set. We don't have more data. We don't have to deal with the subtleties of this. So I wanted to mention it because it is an important practical consideration in some cases, but it's not a practical consideration that we need to deal with here. So actually what we can do is just kind of randomly, we take our data set, we can kind of randomly assign each data sample into either the training data or the testing data. And we'll set a random seed, an integer, so that we can deterministically split the data. So we're going to do it randomly, but in a repeatable way. So that, you know, if we didn't set the seed, then every time we ran this function from Scikit-Learn, which splits the data set into training and testing data, we get a different split. But by setting the seed, we get a consistent split every time. So if you do Shift and Enter, then this, I've got a link here to the Scikit-Learn documentation for the model selection train test split. But you basically provide the data set that you want to split, and then you say, well, what percentage do you want to be included in the testing data set? And in my case, I think I said the test size should be 20% of the data. So the size of our testing data should be roughly 20% of the overall rows. And then this thing called random state is just the random number generator, which controls the randomness. So then, you know, if we run the cell, every time we run it, we'll get the same output because we've set the seed. And then I'm going to add a couple more cells in here. So if we were to look at the training data, so now we can look at the training data and the testing data. Testing data. So remember, our original data set had 20 some odd thousand rows. So 80% of 20,000 rows is about 16,500. And then 20% is about 4,000, roughly. And again, because it's randomness, it's not going to be exactly 80%, no, sorry, it will be exactly 80% and 20%. So you can see here, so now we split, we have this training data and our testing data, and we've split it we've just kind of randomly split it into two chunks. So there's another way that we could split our data into two chunks, which uses, which might be better depending on so of all the variables that we have in our data set, one of them is intuitively, one of them is going to be a very strong predictor of house prices. Does anyone have a hypothesis about which of these, like longitude, latitude, house age, bedrooms, all this stuff, income, which of these is going to have, you think is going to predict median house value the best? So remember, we're trying to predict median house value. So it's not that one, but the other ones. Of the other ones, which is likely to predict median house value the best? So certainly location it's going to have something to do with it. Income. Yes, Basil, income. So if the median income in a census district is really high, probably means that the house prices are going to be higher there too, because people can afford more expensive houses. And if the median income is really low, if people are relatively poor in a census district, then they're probably not going to be able to afford very expensive houses. So probably income is going to be a very important predictor of house prices. So if we think that income is a really important predictor of house prices, then we might want to make sure that the distribution of median income in the testing data set matches closely the distribution of income in the overall data set. And the reason for this is that suppose if median income is really important in predicting house prices, and it just so happens that because of the random nature of splitting training and testing, that we get a test set that has a really unrealistic distribution of income, then that means that our model might perform very poorly simply because the distribution of median income, which is an important driver of house prices, is a bit weird in the test set. So so I see some questions in the chat. I'll circle back to those questions in just a minute. So I just want to make sure that you're understanding the kind of the issue here is that if median income is an important determiner of house prices, then if we end up, because of just randomness of the training and testing splitting process, if we end up with an unrepresentative distribution of income in our test set, then our models might perform really poorly. But the reason they perform poorly is because they're going to be evaluated in a test set that has an unrealistic distribution of income. So we can actually use a technique called stratified sampling to make sure that our test data set has a distribution of income that matches closely the distribution of income in the overall data. And that way we make sure that we don't end up with models that appear to be performing poorly, but only because we have some poorly constructed test set. So to do that, so here's what the distribution of median income looked like in the testing data. Yep. And then here's what it looks like in the overall data. So if you compare these two, you can see that they're pretty close, but they're not. I mean, this isn't a horrible difference in the distribution, but you can see that here there is in our test set there are too few houses in this part of the median income distribution relative to the whole test set. There are too few here. There are too many in this bin and too many in this bin. So we can use something called stratified sampling to solve this problem. And the train test split in Scikit-Learn supports this. So it has an argument called stratify. And we can create this, I'm just going to copy this. So we can use this function from Pandas called cut, which will take it's a way to take a numerical variable and kind of bin it into different bins depending on, and so here I've created bins between 0 and 1.5, 1.5 and 3, 3 and 4.5, 4.5 and 6, and then 6 and above. And Then I've given them labels 1, 2, 3, 4, and 5. And so what this is going to do is it takes median income. Let's see if I can get this to display side by side. Put the comma here. And I'll put this above. Okay, so it takes the median income of 8.32 and then puts it in 5. Well, 5 is the bin corresponding to 6 and above. So this is bin 1 is between 0 and 1.5, bin 2 is between 1.5 and 3, bin 3 is between 3 and 4.5, and bin 4 is between 4.5 and 6, and bin 5 is 6 and above. So if median income is greater than 6, it should be replaced with a 5. And so you can see 5, 5, 5, and then we have a 5.6, and that gets a 4, and so forth. So that's what this cut function does. And then once we have these bins, then the model selection train test split function, when you pass the bins into as the stratify parameter, it will create a train test split where the testing data set, the distribution of the testing data set matches the distribution of the original data set based on whatever you pass in as the stratified sampling parameter. So if we run this, now these are much closer. They're not going to be identical, but the testing distribution is now much closer to the overall distribution in terms of shape. Okay, so in the chat, there is a question. So before creating the train test split, shouldn't we have selected our features? So no. So the feature selection and feature engineering comes after the train test split. Now, I think what you're getting at is that any kind of feature selection and engineering that we apply to the training data, we're also going to have to apply that same process to the testing data before we can make predictions on housing prices in the testing data. And that's true. And we're going to see how to do that on next Thursday when we build up these pipelines. And then once we build up these pipelines, we'll have the same pipeline that we can apply to the training data set that will do all our feature pre-processing and feature engineering. And then when we go to do the evaluation of the test set, we'll apply that same pipeline to the test set. And so any other questions? And I guess the last thing that we do is try to save your training and testing data to disk. So if we run this function, then it will basically write these CSV files, training.csv and testing.csv to disk. So if we look at training, so here's our training data set. And note I kept the original IDs from our original data set. That's important. Let's get rid of that. Okay. So questions about the train test splitting process? So it's really important that to guard against both overfitting and also to guard against, there's something called the snooping bias, which is basically that, if you're not rigorous about doing your training and your testing splits very early in the process, then it can be very easy for information from your testing data set to leak into your training data set. And then all of a sudden you have this model that you think performs great, but then when you actually go and try to use it in the real world with new data, it performs really poorly. So it's really important to have this early and aggressive split between your training and your testing data, and really don't look at the testing data again until you're ready to evaluate your model, so that you don't have any any snooping bias, basically. Okay, so the kind of last thing I want to do today is some more plotting, some more data visualization to try to kind of gain insights into the data. So just give me a moment here. I need to pull up my notes. Okay, so as someone mentioned in the chat, so geography is going to be an important determinant of data or of house prices. So we should probably start by maybe doing some geographic plotting. So here, if we do a scatter plot of the longitude and latitude values. So, you know, this is by no means obviously a finished plot, but it's a start. So we just made a scatter plot of the lat longs for these census districts. And if you roughly know what California looks like, you might think, well, this kind of does look like California. And here's Southern California, like Los Angeles, San Diego. And then this is like the Bay Area, San Francisco, Oakland, San Jose area. And then if you really know your California geography, you might say, well, this is probably Sacramento, which is the capital, somewhere in here. And then there are large empty areas. So Death Valley is kind of over in this area. So that's like a desert. There's not much over there. And then there is a lot of national parks in the mountains that run up in this area. There's a mountain lake that's on the border of California and Nevada called Lake Tahoe, which is this cluster here. And again, you think, okay, well, it's kind of in the mountains. It's not very close to the ocean, but it's near water. So these might be some pricey houses up here. Things to think about. So what we can do when you're doing scatter plots is often a good idea to actually control the transparency of the points in the scatter plot, because then if you do that by setting this alpha parameter, so this is basically setting each scatter to be 10%, 90% transparent, or 10% of the opposite of transparency. But what this does is it actually shows you where the more dense census group areas are. Instead of plotting each point with the same level of transparency, or with zero transparency, so that they're solid dots, which is the case in this plot. If you actually make them very transparent dots, then you can start to see where a lot of transparent dots stack on top of one another is actually where you have density of census groups. And density of census groups corresponds to densely populated areas. So again, you can really see like the Los Angeles, San Diego, San Francisco Bay Area. Now this might actually be Sacramento, and this might be Redding, California. My wife is from California, so my California geography should probably be better than this. I think that is Redding, California. Okay, so now we can do even better. So we can color these dots. Maybe we could change the size of the dot to correspond to something. So we're plotting these lat long coordinates, but can anybody think of something that might be good to one of the variables from our data set that might be useful to use to change the size of the dot? So income, yeah, so that would be one possibility. So there basically dots would be population. Yeah, population definitely would work. So bigger dots would correspond to more populated areas. Yeah. So let's try population. So here in this plot, we are now plotting the size of each dot is proportional to population. So here I basically created, I've taken the population, then I've divided it by 100 just to kind of rescale it a little bit. And then I'm passing in that in as the size of my dots. And then I'm actually using the median house values as the color of my dots. So basically now this is a scatter plot where each dot, larger dots correspond to larger populations, and then the color of each dot corresponds to the house value, which is the thing that we're trying to predict. So like here's an interesting big dot. So it's a dot with lots of population, but relatively low housing prices. So its housing prices are more purplish, so down here someplace. And then here you have lots of yellow dots, but they're kind of medium sized, but the yellow dots are like the 500,000, so these are, like you can see, these are all right along the ocean in Los Angeles, and then right along the ocean in the San Francisco Bay Area. These are all your yellow dots. So there are no yellow dots, up in the mountains. All the yellow dots seem to be relatively close to the coast. So that then suggests that our ocean proximity variable might be very important in determining housing prices, because it seems like a lot of housing prices that a lot of census groups or districts that have high housing prices are indeed close to the water. And then again, this was like the Lake Tahoe area. So there's actually a big lake up here. So even these that are, there might be some yellow ones in here. I can't quite tell, but these are greenish. So these are going to be the expensive California homes on the Lake Tahoe shoreline. And yeah, so the takeaway here is always plot your data and try to think creatively about how you can visualize the variables in your data. So here we started with a simple kind of like plotting of lat long. So Reem asked a question, is there any way to draw on top of a California map? So yes, there is. I just couldn't get it to work in time for today's workshop. So there is a map plotting library, or several map plotting libraries in Python. But the one that I knew how to use has been deprecated and isn't being actively developed anymore. So I didn't want to show you guys how to use that one because it would be useless. And I didn't have time to figure out how to do it with a new one. But yes, the short answer is yes. If you hop into Google, I'm sure you can try and figure it out. Or maybe by next week, I'll have figured it out and I'll fix this notebook so it plots on top of the California, like basically like this plot here. This is the same plot, more or less, but slightly nicer. And you can see, so here's Lake Tahoe there. And this is using a different color scheme, but I'll try to fix this for next week so you guys can see the code to actually do this. Is that somebody with a question or just accidentally unmuted themselves? Okay. Okay, so let's see, where were we? So we did a visualization. Okay. Last thing for today is looking at correlations. So we've done some visual analysis. We've done some like descriptive statistics, some histograms, did some more creative visualizations to try to understand what's going on in our data. And now we're going to look at more numerical measures of structure within our data. In particular, we're going to look at correlations. So the correlation coefficient, we can compute the correlation coefficient, which is a measure of kind of how much do variables in our data set tend to move in the same direction of one another. So one goes up, the other goes up, or in the opposite direction. So one goes up, the other goes down. And we can use the core method to compute the pairwise correlation coefficient for all of the variables in our data set against one another. And so you can see that down the main diagonal of this matrix, the entries are all 1, which makes sense because if you compute the correlation coefficient of a data set with itself, it's going to be perfectly correlated with itself all the time. So the correlation coefficient ranges between -1 and 1. So a perfect positive correlation means that, you know, a variable goes up, one variable goes up, that other variable goes up by the exact same amount. Negative correlation is your variable goes up by some amount, the other variable goes down by the same amount. And then, you know, everything ranges in between. So a 0 correlation would mean there's no linear relationship between these two data sets or between these two variables. And positive correlation means that, you know, one variable goes up, the other tends to go up. Negative correlation, one variable goes down, the other tends to go up. And so then we can look through here and see, so here is a 0.918. So this is very high positive correlation. So there is a strong linear relationship between number of households in a census district and the number of rooms. Well, that makes sense. So if a census district has more households, it's probably going to have more total rooms. That's not surprising. What we would care about is not so much to some degree, it's interesting to look at the correlations between variables that we have to explain house prices, because if two variables are very highly positively correlated, it suggests that we might think about trying to combine them in some way. So for example, total rooms and households, they're both very positively correlated. So maybe what we could do is we could construct a new variable, which might be the number of rooms per household. So we take the total number of rooms and divide by the number of households. And that gives us a good proxy for the number of rooms in a house on average in that census district, which kind of makes sense that, you know, how that might be very predictive of house prices. Because, you know, if you think about house prices, houses that have lots of rooms might have a higher price. And you could think about the same thing for total bedrooms. So total bedrooms and total rooms is also very highly correlated. So you might think, well, maybe we could combine these. So maybe total bedroom, the number of bedrooms per room, for example, might be a good feature. Or the number of bedrooms per household. So let's look at total bedrooms and households. So that's it's almost perfectly correlated. So we could maybe think about total bedrooms per household as being a feature that we would work with. And so we would put total bedrooms per household and then drop out households and bedrooms maybe. So this is the kind of thinking that you should be going through when you're looking at these kind of correlations. And then of course you can look at the correlations from this data frame. If we select out median house value, so this is the last column here, then these are the correlations between our data attributes or our features and the median house value, which is what we're trying to predict. And so we can see here that in terms of the variables that we have, median income is the most highly positively correlated variable with the median house value. Of course, we don't look at median house value itself because it's always going to be perfectly correlated with itself. So median income is the most positively correlated. So income goes up, house prices, house values go up. And then you've got total rooms and housing median age. And then these others are getting kind of small. And then latitude has the strongest negative correlation. So I always get my latitude and my longitude mixed up. So latitude, is this going to be Southern California or more Northern California? Yeah. So latitude. So the latitude is north and south. So what this is saying is that as the latitude values go down, so you go more south in California, property or house prices go up because it's negatively correlated. And so that makes sense because that's basically like saying as you go south in California, you're getting closer to Los Angeles and San Diego. And we know that there are some expensive houses there. And so that kind of makes sense that you see the negative correlation. Okay, so good. We've got some questions. So let me take a look at the questions here. So there's a link to a Plotly library and some bubble maps. So let's take a look at this Plotly bubble maps. So Plotly is a Python visualization package. I didn't actually install Plotly in this environment, but it's a really cool interactive charting library where you can make plots that are, it's not the only library that will do interactive plotting. I do have some interactive plotting libraries in the software stack already, but you can see here, like I'm hovering my mouse, moving it around and zooming in. So let's zoom in here on Saudi Arabia. So what is this a plot of? So this is plotting Gapminder data, which is like economic data. And so it's plotting a dot here. This looks like in Riyadh, and it's giving information about population. And that's down in Yemen. It doesn't look like Jeddah is on here. So, but anyway, so Plotly is a really interesting library, definitely worth taking a look at if you want to do interactive data visualization in Python. And if you were to go to the main website, you would probably find how to install Plotly and Dash somewhere on here. Well, I can't find it right now, but I will. You can install both Plotly and Dash with Conda and or pip in the same way that I've showed you how to install things here. So Ahmed has a question. Does longitude, latitude make sense in terms of correlations with other variables? So Ahmed, I'm not sure what you mean by that. So are you saying that it's not the latitude and latitude itself that is actually relevant, it's some other variables that happen to be correlated with longitude and latitude? In that case, that may very well be true. So this kind of relates to the question that Nabil has, which is, or there's a question about causal relationships that I think from Reem. And this is a very good question, actually a very deep question about causal modeling and machine learning. So most machine learning focuses almost exclusively on what's called predictive inference or predictive relationships. It's building a model that can predict well, where predicting well is determined by our performance metric, which we chose at the very beginning for root mean squared error. So causal relations are not really the driving concern in most of machine learning, not all of it. And actually causal relationships and causal modeling in machine learning is a very active and cutting edge area of research at present. And there's a lot of work on trying to take a lot of the techniques and tools that have been developed in other disciplines for doing causal modeling and bring them into machine learning. To try to kind of leverage the best of both worlds. So you know, in many cases, we want to understand not just like, we want a model that's not just going to predict well, but also a model where we understand why the model is predicting well. But in order to do that, then we have to understand the causal mechanisms, which is actually quite a bit harder than just building a model that can predict well. Let's see, what other questions do we have? So in designing the ML model, can we discard the non-predictive input variables? Yes, absolutely. So this is where designing our machine learning pipeline becomes as much of an art and a science, and a lot of experience kind of goes into it, because, so yeah, you know, if you have variables that don't seem to be very predictive, you can just discard them. And, you know, we'll see examples next week where we can actually create parameters in our modeling pipeline where we can decide to drop or not drop certain variables. And then we can actually automate the process of checking whether dropping or not those variables improves our performance. So that's the nice thing about having a very clear performance metric and doing all of this in code. We can usually automate the process of checking whether or not these various configurations improve the performance significantly of our model. And if it does, we can keep them. If it doesn't, we can throw them out. There's a question about, can you explain how we can build our own Binder account? I tell you, I will give you the link to the Binderhub documentation. Explaining how to do it is definitely out of scope for this tutorial, but the documentation is very good. So here is the links to the Binder docs. And the team is very nice. So they have a Gitter chat, which you can join. They're also on Discourse. You can join either of those and ask questions, and they're very, very helpful and always interested in trying to expand the Binder community. Okay, so almost done. So the last thing I wanted to point out is that, so these correlations are useful, but they're not the whole story, because correlation is a measure of a linear relationship. And to see what I mean by that is, so these are some scatter plots of different correlations. So here's, you know, all these that have 1 are perfect positive correlation, and -1 are perfect negative correlation. And then these scatters are kind of in between values. So this top row is kind of the standard examples of correlation. So you've got a scatter that has kind of a positive slope, a scatter that kind of has a positive slope, but it's more dispersed. This just looks like completely random. But then you go down and you look at the third row. So all these data sets in the third row have 0 correlation, but yet they clearly have strong relationships between the 2 variables in this scatter. I mean, the 2 variables here are making like this wave pattern. Here, you've got some kind of square, but with a tilt on it, and square with a different tilt. Here, you've got like a crescent kind of shape. Here, you've got this very complicated like X kind of shape. Here, you've got a circle. And then here you've got these 4 different clusters. So the correlation coefficient is 0 on all of these different data sets, but there's clearly a lot of nonlinear relationships between the variables. So the takeaway is that just because you, like, for example, if you were to look at so let's say that you looked at total bedrooms, and you said, well, this correlation is very small, so I'm going to throw out total bedrooms. I'm not going to include it. It's not very predictive of my of house prices. Could be the case, or it could be the case that actually the relationship between total bedrooms and house prices is just highly nonlinear and more complicated, and just looks like it's not that strong, but actually it's a really important factor in determining housing prices. And it's hard to know that a priori or beforehand. So this is just kind of a warning about being careful with your correlations. Okay, but we can do some more plotting. So we can do a scatter plot so here's a scatter plot of, it's like the same kind of idea of the histogram plot, but just with scatter plots of our data. And so here we're plotting, so this is a plot of, here's median income in this column against the other variables in the data set. So you can kind of try to look and see, there's not a lot of strong, obviously linear correlation relationships here, but median income and median house values. So here, this one does seem to be like a decent linear correlation. And of course, you've got all these dots here, which correspond to the cap at the house values. So we're going to have to deal with that at some point. And similarly, you can see other areas of like artifacts from the capping that we talked about earlier. So we'll have to deal with that before we can feed these into machine learning algorithms. And yeah, so just another interesting visualization tool. So this one, so what is this? So this is total rooms and median income. Or maybe median income and total rooms. So this one looks like there could be something interesting, but it's a bit squished. So we might want to, maybe there's some transformations that we could do to kind of stretch out the axes a bit. And we'll look at those next week. What? Did my notebook time out? All right. So here's an example of code for single scatter between median income and median house value to kind of, this one is really squished together. So I kind of made it bigger and then made each of the dots a bit transparent, so you can see the scatter a little bit better. And so you can see that this kind of looks more closely to like these two than any of the other relationships in the scatter by far. And again, this kind of makes sense. I mean, income is, so some good questions about how to find nonlinear correlations between inputs and target parameters. So that was a bit more advanced than I was looking to go today, given our time constraints. But there are tools in Scikit-Learn for trying to find different measures of nonlinear relationships. There isn't like there's a lot of different ways that might work and might not, depending on your application. But you will find those in you can look in Scikit-Learn for more information about that. And Mohammed asked a question: is mutual information a better metric for studying dependence? So anything. So I'm not super familiar with mutual information. I'm not presenting, so don't take my presenting of the correlation coefficient here as presenting it because it's like the best way to measure dependence. It's almost surely not the best way to measure dependence because it can only capture linear relations. But it's one of the most common, and it's definitely the first place that you should start. And then when you start going and thinking about, okay, like, are the linear relationships capturing enough of the interesting relations between the data sets, or should I look for something that is more nonlinear? Or then you can go and look at these more kind of advanced and newer ways of capturing dependence. Okay, so the last thing that I want to do is just talk a little bit. This is like the bridging topic to next week. So experimenting with combinations of features and attributes. So this is kind of our first baby steps into feature engineering. And we're going to talk about how to kind of automate this and tighten it up next week. And so Yazid says, I think the line up in the graph is messing up the correlation. So that is almost surely like, we're still including the capped values for a lot of these variables. So if you drop the observations with the capped values, then the computed correlations would definitely change. Yep. And the reason that I've kept them in so far is that next week we're going to talk about how to drop them, but in a more principled fashion as part of our analysis pipeline. So a lot of what we've been talking about here, we're going to do some of it next week, but we're going to do it in a way where we can automate the process. So I didn't want to get into dropping these things just yet because we're going to do that next week. So baby steps into feature engineering. So here I'm thinking about combinations of variables that might be better predictors than the individual variables themselves. So things like, instead of looking at total rooms in a household separately, maybe it's better to think about the number of rooms per household. So, proxy for number of rooms per house. And then this one is like, would be a proxy for ratio of bedrooms to total rooms. So these are things that might make more sense. So unfortunately, we don't have any information on the number of bathrooms, because then that might be, you think about other things that might drive housing prices. So like having the right ratio of bedrooms to bathrooms might be important in determining housing price. So if you have like, a house with one bedroom and 6 bathrooms or something, that would be a bit weird, and might, like, who would buy a house with 1 bedroom and 6 bathrooms? So you might think that house must be very low in price. Or if you had similarly like a house with like 10 bedrooms and only 1 bathroom, then that's also a house that's probably going to have a very low price, because that's going to be difficult. So that would be an example where you would have this kind of non-linear relationship between a variable where like extremes on either end would be low house prices, and something in the middle would be a better, more expensive house, having like the right ratio of bedrooms to bathrooms. But unfortunately, we don't have that data. And so this would be like, this is almost a proxy for population density. So here we're taking like how many people are in the household. So this is like, are areas where there are more people per household likely to be areas where housing prices are higher or not? And so here I'm just showing you how you can create these data, or these new features, by hand, and then add them to your data set. And so now we can look and see that, so the rooms per household is more strongly correlated with median house values than either total rooms on its own, and much more correlated than households on its own. And then similarly, what were some of the other ones that we did? So we looked at population per household. So population per household here, it's not actually clear that this one would be a super useful, because population on its own had a stronger negative correlation than population per household. So I'm not really sure that one is actually doing that much for us. But could be that the relationship is more nonlinear. is not being well captured by, it could be that the relationship between population per household and house prices is not well captured by correlation, because it could be that it's very nonlinear or something. Right, okay. Oh, and look at bedrooms per room. So before we had, so the number of bedrooms was only, had this kind of small positive correlation, and the total number of rooms had a slightly larger positive correlation. But now this bedrooms per room metric is strongly negatively correlated. And so this might suggest that this kind of bedrooms per room, like having is, well, what it suggests is that having a very high number of bedrooms per room means a lower housing price. But then I wonder if this is also could be a nonlinear relationship that's not really being well captured by correlation. So could it be that if you had a large number of bedrooms per room, you might have a lower house price, but also if you had a very small number of bedrooms per room, you might have a lower house price. So it could be that there's like this sweet spot ratio in number of bedrooms per room that makes for a strong or a high house price. So it might be that actually that bedrooms per room is a good feature to have, but it might turn out that when we start fitting models, that you might need a model that can capture a lot of nonlinear relationships in order to take advantage of this bedrooms per room feature well. But again, for next week. Okay. So that's all I wanted to cover this week. So I will, so before next week, I will upload the notebook for next week to the same repository. It'll just be called Part 2. It's probably not going to be uploaded until maybe like Wednesday of next week, because I'm probably going to be working on it and tweaking it and trying to improve it. Or I will upload many versions next week, and you might want to check back later in the week to get a better one than what you'll get early in the week as I continue to kind of improve it. But next week, we're going to talk about preparing the data for machine learning algorithms and training models, and how we're going to train multiple different kinds of models and show how to select basically one of those models. And then we're going to talk about how to fine-tune models, basically, and then we'll wrap up. So we're going to be talking about a lot of different parts of Scikit-Learn next week. And thank you very much for spending time with me this afternoon. And I look forward to seeing everybody again next week.
Thank you, Dave.
The video recording from today's session will be up on, well, I'll probably put it up sometime this weekend. And we'll share the link with you next week. So I'm happy to hang around if anybody has any questions for the next 10 minutes or so.
I appreciate your effort. Thank you so much, Mr.
You're most welcome. Thank you for coming.
So David, the link of the recorded session here will be shared with us.
So it'll be on so I can share you with the link with the YouTube channel.
No, I mean our session now. So.
Oh yeah, so it will be shared with you. But I'm just letting you know that it will eventually be. Where did I put? I know there's a link to our YouTube channel here somewhere. Here it is.
Oh, okay.
I'll put it in the chat.
Thank you, David.
You're welcome. So it's eventually going to show up here at some point this weekend. But I will also send out an email which will include the link directly to the video as well. Any other questions? Okay, so if there's no more questions, then I will see you guys next week. Thanks for coming along to the training today.